Hello, welcome to Math321. This is multivariate polynomial interpolation. Multivariate polynomial interpolation is a bit of an awkward affair. There's quite a bit of research on Lagrange polynomials in multiple dimensions, and their uniqueness is no longer guaranteed by a fixed number of points. It depends upon how those points are arranged in the plane. And that makes life difficult. The techniques I'm going to show you are just examples of what can be done. If you're ever in the situation where you do need to interpolate a multivariate polynomial, my best advice is to see if you can read the literature yourself. I'll give you some places to start off with, but it's not a clear-cut science, if that makes sense. The previous results you've seen in one dimension don't really carry over to one dimension quite as nicely, but it's not as bad as all. There are some things that can be done. So, for example, in the one-dimensional case, we had piecewise linear interpolation. And you can do that in this case. So here we have R2 and a bunch of points over R2. We might divide this space up. We could divide the space up by how close you are. So we divide it up into regions. However you want to. Like this. So divide into regions. SI. And define our polynomial from, in this case, R2 into, let's say, R by P of x is equal to xi if x is an element of SI. So the regions have to be separate from each other. Now, if you define, if the SI are defined by SI equal to x inside R2, and this would work just as well for Rn, so that of course, here the xi's are vectors, I mean two-dimensional vectors. Anyway, so if the SI are defined like this, then what you end up with is called a Voronoi diagram. In a sense, each SI here is defined as the collection of points which are closest to xi, so their value should be governed by xi rather than anything else. For example, sorry, it's piecewise constant. Piecewise linear here we have points all over the plane again, and we chop it up however we want to. Each SI is given by 3 points. So we define Pi, the interpolant on the SI piece, is going to be equal to AI0 plus 0, 0, AI10 x plus AI0, 1 y. And you have a system of 3 equations, xi, yi's equal to fi, where we have the points x, I, x, I, y, I, f, I, and the notation over here is really xi is equal to some xi and some yi, a vector, right? So I should probably say something to indicate that these are vectors. And the polynomial. Right, so that's piecewise linear. And of course you can do that in higher numbers of dimensions by adding on extra points. So in Rn, the interpolating polynomial pi x1 up to xn is given by f1, well, some value of the function, which will be some ax1 plus bx2 plus all the way up to some exn plus some constant thing, g, whatever. N plus 1 points, if we're in n dimensions and we have n plus 1 unknowns, plug them in, solve them. So piecewise interpolation is not so bad. You can definitely always do that. So for example, bilinear and trilinear, you do it the same way. A bilinear interpolant would be pxy is equal to a00 plus a10x plus a01y plus a11xy. Bilinear interpolant. And trilinear, and so on and so on and so on. Yeah. If you fix the grid specifically, and so on, then it can be easier to work out or to write down explicit formulas for what's going on. You interpolate in this direction, or in the y direction, and then interpolate the functions and the result is you get things that look like this for linear interpolation. So, for example, if I have some y0 and then I interpolate in the x direction, then I end up with a function that looks like this. I'm doing linear Lagrange interpolation, which means I'm working over a square. So we interpolate for the other y. And then we interpolate between those two functions. Which gives us an interpolant over the whole square and everything inside. If you rewrite this out, then you get something that looks like this. hopefully the pattern is becoming familiar. Of course, that can be written as I said, a00 plus a10x plus a01y plus a11xy. Is there a specific formula for the a's, the coefficients in this case, like we derived in the one-dimensional case? Yes, there probably is. Am I going to write it down? No, I'm probably not. It's a lot of work. I'm definitely not. But you can try, and you might learn something, I suppose. Error for this particular case. Error in general for multi-dimensional polynomials is again awkward, but in the case where you're dealing with a fixed grid like we are, then you can actually say something worthwhile about it. And it essentially boils down to using the individual error results for our polynomials interpolating for a fixed y and applying that to our b. So for example, for previous results we know already that fxyi minus pyi x is equal to 1/2. Right, and then when you consider what the definition of bx y is, then you can write down I'm going to call this thing error yix. So you can call this, so you get the error in the y direction because we have y interpolation going on. As you expect, plus 1/2 times the interpolation in the y direction, or the Lagrange interpolant, times the error, the yi error x 0. This is less than 1, and that's going to be less than 1 because we're dividing by the step size here. So you can always say that the absolute value is less than or equal. There's two lots of these. We bound them in the appropriate way, then we can say this is 1/2 max. And the half here is an artifact of first interpolating with respect to x then rather than with y. But from the formula of b, we know if we interpolated with respect to y first and then with the interpolate with respect to x for the functions that result, we get the same function because it's symmetric in the x's and the y's. So this bound is not the best that can be done. This also happens to be less than by doing the process I just discussed. And if you do that, and you look at a little bit of algebra, I'm going to call this term here, as I'm going to write by A, and this term here I'll write by B, then what you can actually show is that which is a better bound than all of the estimates I've done so far. It can actually probably be improved further as well, but I'm not going to investigate that. And there are plenty of results talking about error in multidimensional situations of polynomials, and in particular for Lagrange polynomials. And remember, that's yeah. Okay, trilinear. So my data points look something like this with an fi, and the b, x, y, z. If you interpolate an x, and interpolate y, and interpolate blah blah blah, is going to be equal to, and it's literally what you expect. Plus all the other combinations of things. And this is equal to a000, a100x plus a010y plus a00yz plus blah 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 blah. And you can determine the coefficients just by plugging in the values, because we know that b, xi, yi, and zi has to equal fi, and so on and so forth. In this particular case, we're looking at interpolating over a cube. And of course, you can do the same thing with higher order polynomials as well. We could do it with cubics, for example. Here, our pxy is going to equal the sum ij equals 0 to 3, aij xi yj. This gives 16 unknowns. So you need to have some conditions for this, and to do that, you can match derivatives. Derivative of f with respect to x is going to be the derivative with respect to x of p. Derivative with respect to y of f will be the derivative with respect to y of p. We'll take the second partial derivatives. Yep, and of course p xi yi has to equal fi. So that's 4 equations, and we've got 2 of everything, so that gives the appropriate number of unknowns, and you can solve them. At this point, just plug in the values, get some linear equations out and do them. And you can do all sorts of different combinations, extend all of those techniques to all of the various degrees that you want. And it gets very complicated because there's lots of equations, lots of unknowns, and so on. Use a computer. Okay, so here's the last example I'm going to talk about, and these things are very useful. And they are used all over the place, radial basis functions. The idea is that with xi's and fi's inside Rn plus 1, fi an element of R, then we define the interpolant as a gx is equal to the sum over all the points that we know about, that we have, with a coefficient in front times some function and the distance from our point that we're interpolating to the xj. To solve this, we know that gxi equals fi, and that's going to be equal to the sum j equals 0 to n of my alpha j's times f at 5, 0. That's a constant number. We have a linear system for the alpha i's. Solve it, get the answer. So what do these things look like? Essentially, the idea is that if you have a data point and some value, then you pick some function that describes the influence of that measured value. Very roughly, if you know that your function is continuous, then you know that close to that measured value, the function should take a value close to it. That's what these are trying to do. Add them all up. So you end up with a sum of bumps. Examples. So C here is sometimes called a shape parameter, and in some other contexts sometimes it's called a bandwidth. Bandwidth and the shape parameter describe how quickly does the influence of a particular measurement fall off in your multidimensional space. So if you have high C, you're going to have something that looks like this, and if you have low C, you'll have something that looks like it's a bit more spread out. So the idea is to represent the real value of the function as a series of bumps in your multidimensional space, and add those together. Each of those bumps is going to estimate the value of the function itself at the particular point where measurement occurred. So the sum should estimate the whole function itself. Now, there's plenty of examples of these kinds of functions, and they are used all over the place. I'm going to talk about a particular example which is used in non-parametric statistics called kernel density estimation. So this is a circumstance where you have a random variable and you've taken measurements of it, and you want to estimate that probability density, the probability density function for the random variable. Here are examples of what are called kernels, which are essentially radial basis functions. Note that there's no shape parameter in each of these, and essentially that's incorporated by saying that the probability density function is a sum over these things where you do this. It's important we don't worry about the sign here, because we have these indicator functions to control the actual size of these things, of the terms. And the h here is the bandwidth, and it acts in the same way as the shape. So, for example, I'm studying right at the moment some papers that came out applying kernel density estimation to determine the probability density function of the volatility for certain derivatives. It's a very basic technique. Works well. You don't need to know that your measurements are in a grid. You don't need to know special relationships between them. I think it's kind of nice. And that is multivariate interpolation.